Okay, folks, just a quick reminder of what we talked about last class. We were talking about modifying the idea of Burnside's limit to keep track of the cycle lengths. So, we had these variables xi, and it stood for a cycle length of length I. So we were talking about D8. Sometimes it's called D4. There's no standard notation for it, but it's the rigid motions of the square. The identity does nothing, so 1 goes to 1. That's a cycle of length 1, and same with 2, 3, and 4. So we associate that with the variables x1 to the power of 4. And similarly down here, something like rho sigma here. So you can check that rho sigma is like a flip through the vertical axis. So 1 gets sent to 2, 2 gets sent to 1, that's a cycle of length 2. And 3 gets sent to 4, 4 gets sent to 3, that's another cycle of length 2. So we have this cycle being represented by x2 squared, and similarly for all the other cycles. Now, we could do the same thing with Burnside's lemma. We can just add up all of these cycle length variables, and you can check we get this polynomial here in the variables x1, x2, x3, x4, and we just keep that 1 over the size of the group on the outside as well, and we call this the cycle index of the group itself. And as we said before, we can recover Burnside's limit just by setting each of the variables equal to the number of colors you can color each object with. So here, we set these equal to 2. So we plug these in here, and we get that there are 6 colorings of the square up to rigid motions. And by colorings of the square, I mean colorings of the vertices of the square. We could do the same thing with n colors instead of 2, no problem. Just replace 2 by n. And we were working towards doing a little bit better than that. The whole idea was we want to keep track of the colorings themselves and not just the number of colorings. So here, if we set x1 equal to b plus r, we're thinking of this as blue plus red. We saw that if we plug in b plus r into x1, then we get x1 to the 4th is this expression here. And each of these guys represents one coloring that indeed is fixed by the identity. All blue, there's 4 colorings, which are 3 blue and 1 red. 6 colorings that are 2 blue and 2 red. 4 colorings are 3 red and 1 blue. And there's a coloring that is all red that are fixed by doing nothing. And that is, of course, all of our colorings. And similarly, we found that if we plug in b squared plus r squared for x2, thinking of x2 representing 2 cycles, then x2 squared, remember, the cycle type x2 squared, that represented rho squared, so rotation by 180 degrees. If we multiply that out, we get b to the 4, r to the 4, and 2b squared r squared. And these are indeed colorings fixed by the rotation by 180 degrees. All blue, all red, and 2 of them, which are 2 red and 2 blue. In fact, these guys here. And you can imagine a similar thing. The other ones with cycle type x2 squared were the horizontal flip rho cubed sigma and the vertical flip rho sigma. So these guys here are indeed very similar. We'll find we get everything being the same colors fixed, and there are 2 colorings which are 2 blue and 2 red, which are fixed. So we can indeed generalize this. So the whole idea here is however many colors we have. Let's say we have R colors instead of 2 colors like we had before. We can have however many colors we like. We can make a substitution in for, we're thinking of this guy as subbing in for xj. And all that's going to be is the same idea as we did before. It's each color to the power of the length of the cycle. So we do that. So that's our kj here. And then plugging that in to our cycle type, so rather than plugging in the x's, we plug in that nice substitution. That gives us the generating function for all colorings up to the group action. And not only that, it gives us not just the numbers, but it also gives us the types of colorings, the patterns of colorings as well. For example, in our polynomial for coloring the vertices of a square with 2 colors and with rigid motions of it as our group action, we have the following polynomial. So we plugged in b plus r for x1, so we have x1 to the 4th, and then 2x4, so we plug in a b to the 4th, r to the 4th, and then etc. So we keep doing that for each of the variables here. x2 squared, x1 squared, x2. And if we simplify this, if we multiply this out and simplify it and then divide by an 1/8, you can check that what we get is the following. And what's really nice is this tells us specifically each of the 6 colorings that are possible up to the group action. So here's all blue, here's all red. We have a coloring that is 3 blue and 1 red, and by group action we can get to any of the other colorings that are 3 blue and 1 red, and then similarly 3 red and 1 blue. And then we have 2 different types of colorings that are 2 blue and 2 red. There are the ones where they're next to each other, like that, or the ones where they're separated, like that. So this polynomial gives us a lot of information about the possible colorings. So up to the action of D8 on our colorings, there are 6 unique colorings, and on the last slide we saw that that polynomial kept track of the types of them, the patterns of them. And in fact, in a lot of cases, people call this the pattern inventory of the colorings of our set X. So this polynomial PG with those K's, making that coloring substitution, that's called the pattern inventory. And another nice simplification we can make, sometimes we're unconcerned with one particular color, we're just concerned with the other, or maybe we're concerned with 2 and not the third, or maybe we're concerned with 1 and not the other 2. Any of the colorings we don't want to keep track of, rather than substituting an actual variable in that, or coloring, CI, like a B or an R, we can just put a 1 in there. And then when we multiply things, those 1s just get multiplied to 1, and they go away. So for example, if we only wanted to keep track of the ways you can color the vertices of a square with blue, and we didn't really care about red, maybe we'd make the substitution blue plus 1 and blue squared plus 1 into our and we need the other ones as well, sorry. We also need blue cubed plus 1 and blue to the 4th plus 1. And if we did that, you can check yourselves, you get the following. You'd get b to the fourth plus b cubed plus 2b squared plus b plus 1. And this kind of forgets the information about the r's now. The r's just get set to 1, right? So all of the r's that were in this polynomial before get set to 1, so now it only retains the information about the b's. So if all we care about are the b's, there's one coloring that's 4 blue, there's one coloring that has 3 blue, there's 2 different colorings that have 2 blues, one coloring with 1 blue, and one coloring with no blues. Okay, let's see how we can use this idea of Polya enumeration to be able to count some things that appear in real life. And the first example that we're going to do is about music. So, a musical octave consists of 12 notes. If you've seen a piano, this is probably very familiar to you. But it goes C, C sharp, D, D sharp, E, F, F sharp, G, G sharp, A sharp, B. Some of these notes have alternate names. You could call this D flat or E flat, whatever. But for our purposes, we're not too concerned with that. We can consider these just numbers. 1, 2, 3, all the way to 11, 12, or 12 notes of the octave. And we're interested in 3-note chords, which we'll call a triad. And it's just some combination of 3 of those notes. And I think a very common one, if you've played any music or you know anything about music, something like C, E, G is an example. That's a major chord. That's C major. But we don't want to count D, F sharp, A as any different. Since that's D major, it's just a transposition. It's just moving around the circle. You can see here that if I start at C, E is 1, 2, 3, 4 notes up, and then G is 1, 2, 3 notes up from that. But the same pattern holds if you start on D. If we go 4 notes up, 1, 2, 3, 4, we get the F sharp, and 1, 2, 3, we get the A. So we'll write this out in a circle in a bit, but I want to count these guys as the same chord. Also, I'm not particularly worried about inversions or anything, so I don't care about starting on C or E or G. So let's call these guys equivalent. I also want to call something like E, G, C equivalent as well. That's called an inversion of a chord in music theory. So we know there's a major triad. You know there's also a minor triad, so that's just something like C, or let's write it like this, A, C, E. If you know anything about music, you know that's a minor triad. And there's lots of other triads, but the point is, how many different triads are there? Again, we only care about the notes in it, not the order of the notes, and we don't care about where they start. We only care about kind of their pattern around the circle. So we want to know up to transposition, or you can think of it as key change if you like, or if you don't want to think about it in music at all, you can think of it as rotation around the circle. How many different triads, these 3-note chords, can be made? Okay, so we want to use Polya enumeration here. So we want to have some group acting on some set. So let's go ahead and think about this. Our underlying set, well, that's just going to be our notes. That's what's being moved around. So the underlying set, we're going to think of it rather than as C, C sharp, D. We'll just think of it as the numbers from 1 to 12. So that's going to be our underlying set. And we have to ask, well, how can we act on this? And we want to identify, if you like, chords that are just transpositions of each other by rotating around the circle. So we want to act on these 12 notes just by rotations. So we're going to say that our group is just the rotations of 12 things, which we call C12. And so we'll think about this as, let's call it the identity, of course. That does nothing. Then we have row, row squared, row cubed, all the way up to row to the 11th. Now we have to think about what's going on here, how we can use the idea of Polya enumeration to help us out. So let me scroll here. I'll make a little bit of room. So let me draw a circle. There's a circle, I guess. And I can plot some points. Bear with me here. I realize this isn't a perfect circle, but that's okay. We don't need it to be. This is just for elucidation purposes. So there's our circle. And let's label the vertices maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And remember, we just want to act on this by rotation. We don't want to invert things. We don't want to flip notes or anything like that. So we don't want to act on this circle by rigid motions, just by rotation. Great. So the chord C, E, G, if we think of 1 as the note C, then we can think of C, E, G being this note C, and then C sharp, D, D sharp, E, F, F sharp, G. So we can think of this as C, E, G, or if you like, 1, 5, 8. So that's one chord. And if we acted on this by maybe, let's say, row squared, so that's a rotation of 2 bits. So 1 would go to 3, 5 would go to 7, 8 would go to 10. Maybe I'll do this in green. So there's row squared acting on it, rotating twice. So we get 3, 7, 10, which we can say in notes, if you like, as D, F sharp, A. But my point is we want to count them as the same. They're just a major chord. Again, if you don't know anything about music, that's fine too. All we want to say we can get from 1, 5, 8 to 3, 7, 10 by acting on that coloring via row squared. So you can start to think what's going on here. We're picking 3 notes or coloring 3 notes and not coloring the others. So maybe what we want to do is we want to look at some generating function that enumerates all of the different ways of coloring these notes for different numbers and then identifying these by our group, by the action of the group. So a good tool to do that would be that pattern inventory idea. So maybe our idea is, let's find the pattern inventory. And we want, let's say we want 2 colors. We want, let's say, maybe a red. That's our notes that we care about. And we have notes that we don't care about, and we don't even want to keep track of those. So maybe we'll let them equal 1. So that will be our colors. Red and something we don't care about, we'll call it 1. And we want, because we want to figure out how many triads there are, we want the pattern inventory let's say for our 3, because we want 3 reds. So that's going to be our goal. We're going to do the exact same thing as in the last example. We're going to build up all of our cycle types for each cycle, and then we are going to assign variables to those. Then we're going to plug in appropriate k's, if you will, into each of them, simplify, and just see if we can figure out what the coefficient for the r cubed term is. Okay, so obviously we have 12 permutations, so we'll just go through all of them. A lot of these will have the same cycle types, so rather than kind of working out 12 individual ones, we'll notice something about patterns, and we'll be able to do a bunch at the same time. Well, the identity obviously does nothing to all 12 of our notes, so we have 12 one cycles, so we will denote that by x1 to the 12th. Now let's look at row. Row sends 1 to 2, 2 to 3, 3 to 4, 4 to 5, to 6, to 7, to 8, to 9, to 10, to 11, to 12, and back to 1. So that is indeed a 12 cycle. And we only have one of those. And if we think about it, well, if we rotate in the other direction, it'll still be another 12 cycles. So row does this, and so does row 11 row to the 11 behaves similarly. So these will be the similar ones in red. And if you think about it a little more, row to any power that is co-prime to 12 is going to give you a 12 cycle, because there's no common factor to get back to make an entire closed cycle besides 12. So the other two numbers where you'll have 12 cycles will be row to the 5th and row to the 7th. Great. Okay, so we looked at row. We got row to the 5th, row to the 7th, row to the 11th. Now let's look at rows squared. So row 1, so it moves 2 places, so it goes to 3, which goes to 5, which goes to 7, which goes to 9, which goes to 11, which goes back to 1. And then we have 2, 4, 6, 8, 10, back, or 12, sorry, missing a 12 here, back to 2. So that is indeed 2 6 cycles. So we have x6 squared. So that is our row squared. I'll just put a line here just to make sure that I'm not getting a little too messy. And the other ones that behave like this, and if you think about it, it won't take you too long to think about it, any time that the GCD of the power and 12 is 2, then it's going to be split up into these 6 cycles, 2 6 cycles. So our other numbers that operate like that are row to the 10, and that is indeed it. Maybe I'll write row to the 10 in red, just to say that this is one that behaves the same way, even though the cycle type is for the black one. And you can check maybe if you want to make sure. Work out the cycle type for row to the 10th. You can just go around the circle and think about what's going on that way, and you should see that it's 2 6 cycles like we have here. So how many do we have so far? 1, 2, 3, 4, 5, 6, 7. So there's 5 left. Let's look next at row cubed. That's the next one we don't have. So 1 goes to 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, back to 1. And then we have 2, 5, 8, 11, and 3, 6, 9, 12. So our representation by variables is going to be x4 cubed, since we have 4 cycles. That's great. And with the similar logic to before, the other rotations that have the same cycle type is going to be rho to the 9. The greatest common divisor of 9 and 12 is 3. So when we're just rotating, we're just, hey, this has 3 cycles. So that tells us that. Great. So we're almost done. We have 2 more. So let's look at rho to the 4th. 1 goes to 5. 5 goes to 9. 5, 6, 7, 8, 9. 9, 10, 11, 12, 1. So that's a 3 cycle. And you can check. We get 2, 6, 10, 3, 7, 11, and 4, 8, 12. So here we have 4 3 cycles. So x3 to the 4th. And the other one that behaves like that, you can check again with similar logic to the ones above, is x to the 8. And finally, well, there's only one left, and that is rho to the 6th, so a half turn. And what's that going to do? That is going to send 1 to 7, 7 back to 1, 2 to 8, 8 back to 2, 3 to 9, 4 to 10, 5 to 11, and 6 to 12. So here we have 6 2 cycles. Okay. And we have everything. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have all of them. Great. So I called my colors here A and B, but on the previous slide I called them, well, red and I guess nothing. So maybe instead of A, let's call that 1, and instead of B, let's call that R. So that's our color set. Again, just putting a 1 in for something that I don't want to keep track of. So we're good there. So each of our KJs is going to be 1 plus, I said B before, but let's change that to R to the J. Great. So next, let's write down our P sub C12 on our 12 element set and go from there. So we need our PC to 12. So we know this is going to be, maybe I'll write this in blue. So it's going to be a 12th 1 over the size of the group. And then times each of the cycle types represented by the x's added together. So we had 1 x1 to the 12th. And then we had 4 of the 12 cycles. So that was when we had rho to the 5th, rho to the 7th, and rho to the 11th. So in each of those we just had 1 12 cycle. And then we had our 6 cycles. That was rho squared and rho to the 10th. So we had 2 of those. So we had we had 2 x6 squared. And then we looked at rho cubed and rho to the 9th, which were the same, which gave us 4 cycles. So we had 2 x to the 4 cubed. And then we had rho to the 4th and rho to the 8th, which were 3 cycles, so x cubed to the 4. And finally, we just had 1 that was a bunch of 2 cycles, in fact, 6 2 cycles. And that was for rho to the 6th. So there is indeed our cycle expression for this situation. So now we can decide how we want to color it and what colors we want to keep track of, just like before. And we already said that we're going to let our ki's, this is going to be 1 plus b to the I. So let's write this in, and I don't want to just expand it out fully. You could do that, and you would get the correct coefficient, but we can do a little bit of reasoning so that we don't have to do any extra calculation. So let's go ahead and do this. So we're going to get 1/12, and then we have x1 to the 12th, so this is going to be 1 plus r to the 12th plus 4x to the 12th, so that's going to be, 4x12s to the 1, so that's going to be 1 plus r to the 12th, so we have 4 of those guys. And then we have 2x6 squared, so we have 1 plus r to the 6th squared, and we have 2x4 cubed, so 1 plus r to the 4th cubed. And then we'll write on the next line, or we only have 1 left? No, we have 2 left. So we'll write on the next line, plus 2x3 to the 4th, so 1 plus r cubed to the 4th. And finally, we have 1 plus r squared to the 6th. So there's our pattern inventory without expanding it out. And I'm interested in the coefficient for the r cubed term. So let's scroll up here and write that down. So interested in the coefficient for the r cubed term. And in a lot of cases, there's just going to be no r cubed terms in that term of our expression. So for example, this guy here, 1 plus r to the 12th, there's no way an r cubed is going to appear. So I don't even need to look at this guy for now. So I'll put a little cross there to say that that's not going to be important to us. Same with this guy. The only things are going to be are r to the powers of multiples of 6, since we have 1 plus r to the 6th to powers. So we don't have to look at this guy. Same with this guy. 1 plus r to the 4th. And this guy we can get an r cubed, but this guy we can't, right? Because we have 1 plus r squared to the 6th. So all of the r's are going to have even powers, and we're looking for an odd power, so we don't need to include that guy either. So the only places where we can get coefficients for r cubed are here and here. So indeed, I can use, for this guy, I can use the binomial theorem. Actually, for both of these, I can use the binomial theorem. So let me call this guy, I guess, 1. And this guy will be 2. I'll figure out the coefficients in both cases and then add them together. So for 1, and I guess I should say it's going to be 1 plus 2. Okay, so for 1, we want the coefficient for r cubed. So remember, the binomial theorem says we're going to go from n equals 0 to 12 of 12 choose n, 1 to the n r to the 12 minus n. So I'm looking for r cubed here. So obviously n's going to be 9, or you could just reverse these and have r to the n, 1 to the 12 minus n. Doesn't really matter. But because 12 choose 3 is 12 factorial over 3 factorial, 9 factorial, and 12 choose 9 is the exact same thing. So, of course, there's that symmetry going on there. So, let's set n equal to 9 in this case. So, we're looking for 12 choose 9. So, let's write that out. That's 12 factorial over 9 factorial, 3 factorial. So that's 12 times 11 times 10 over 6. So what do we get there? We get, well, 12 divided by 6 is 2. So just to simplify my life, let me do that. And you can see that 2 times 11 times 10 is going to give you indeed 220. That's good so far, so that's 1. And remember, we're going to divide by a 12th as well to get that coefficient. So maybe I'll even write that here. 1 plus 2 divided by 12, since we need to divide our polynomial by 12 at the end. Okay, so that's case 1. Well, case 2, similar thing, except now our variable is r cubed, not just r. So we have 2 times the sum, and n goes from 0. In this case, it's now to 4 of 4 choose n. And we have 1 to the n r cubed to the 4 minus n. And if we're looking for a coefficient of, or sorry, a power of 3, then we want 4 minus n to equal 1. So we're looking for when n is 3 in this case. So we'll set n equal to 3. And we have 2 times 4 choose 3. And then r cubed. Well, I don't even need to write that because I just need my coefficient. So 4 choose 3 is easy. That's 4. And 4 times 2 is indeed 8. So that's great. So let me scroll here. So we have 1 plus 2 divided by 12 is 220 plus 8 divided by 12, which is 228 divided by 12. And it's fairly easy to check. You can use a calculator or just do this by long division or even just by inspection, that our coefficient is indeed 19. So this way we were able to tell that there are indeed 19 different triads. Up to transposition in music, which is great. And keep in mind, there was nothing special about 3 here. You could ask maybe, well, a major scale has 7 notes in it. How many different 7-note scales are there? Then we would just go all the way up here, and we'd ask, instead of how many, what is the coefficient of r cubed, we would be looking instead for the coefficient of r to the 7th, which I guess would come from this guy, and maybe that's the only one, actually. So that's pretty interesting, because none of these guys here have any way of giving you a power of r, which is 7. All of these are multiples of 12, 6, 4, 3, and 2, and 7 is prime. So your 7 would just come from here. And, well, that's easy enough. In fact, we can just do that. So this is going to be 12 choose 7. That's how many 7-note scales there are. And I believe this is 792. And, of course, I forgot we need to divide by 12. So this should be 12 choose 7 divided by 12. And if we divide that by 12, we indeed get 66. So there are 66 different 7-note scales in an octave. So that's really, really interesting. And again, that's up to transposition. So you don't want to count major scales differently from each other. We want to say that they're the same flavor of scale, just transposed. Divided by 6. I'll leave the following as a little exercise for you. But let's say we have a 3 by 3 square. So it looks like this. And we'll label it like this. 1, 2, 3, 4, 5, 6, 7, 8, 9. Or 3 by 3 square that we cut into sub-squares, however you want to call it. And each of these segments can be colored one of 3 colors: blue, red, or green. And I want to know how many colorings exist up to rigid motions that have exactly 2 blue, 3 red, and 4 green squares. So, again, I'm leaving this as an exercise for you, but what I've already worked out is the following to give you guys a hand. Remember, this is rigid motions of a square, so we just need to figure out the cycle types as they act on these 9 subsquares. What happens? So I've worked this out for you. You guys can check it, but let me scroll up again. So let's just see the rotation rho. What is rho going to do if you rotate this 1 turn clockwise? Well, 1 is going to go to 3, 3 is going to go to 9, 9 is going to go to 7, 7 is going to go back to 1. So that is that cycle. And then 2 is going to go to 6, which is going to go to 8, which is going to go to 4, which is going to go back to 2. So that's that guy. And 5 goes nowhere. So 5 is fixed under rotations here. So I think it's in your interest to check that you understand that these are indeed the cycles of these 9 subsquares of our main square that are induced by D8 here, or D4, however you want to say it, the rigid motions of a square. So check that you understand where these are coming from. So I'm giving you these, and we'll move on to the next slide. And you can check here that this is indeed our cycle index function for the way that D8 acts on these 9 objects. So that's fantastic that way. And of course, we know that our colors are blue, red, and green. So I'm going to say B, R, and G. Maybe I'll write them in black, not a different color, so it doesn't look like they're colored. And so that's going to be this is our K1. We don't have an X2, or we do have an X2. Here's our X2, etc. So we can just fill in our Ks for our X's. And the thing that I want you guys to work out is I want the coefficient, because remember, we're looking for how many colorings exist with 2 blue, 3 red, and 4 green. So try and analyze this term by term in order to find this coefficient. B squared, R to the third, G to the fourth. Remember that once you kind of figure out for each term here, you can add them together. And then once you add them together, remember you have to divide by 8 here to get that. So I'll leave that as a little exercise for you guys.